All right, this is going to be the CAD walkthrough of the Eye of Agamotto, the latest version. So, like I said, about 3 years ago, I developed this version of the Eye of Agamotto. And I thought I would just very briefly explain how this one works, and that'll hopefully bring some context to the new one. So, this one, it's actually all bolted together, which I guess, demerit number one. So, that is something that I wanted to improve on the new one. But let me hide some of these faces so we can talk about how it works. So the front cover and the back cover were both integral to how it works. So you could very carefully paint it and then realize you needed to tweak something or accidentally break it, which is a terrible feeling. So I knew I wanted to change that, and I did change that about the new one. For this one, it uses a servo motor, right? This gear spins, which spins this gear, and it kind of goes across this whole plate through this gear and then through a bunch of other gears to get these rings spinning. This design, there's 4 of these arcs. I coupled 2 of the arcs together. So there's a set of 2 on top and a set of 2 below it. That was to simplify the mechanism, and my original intent was to, have that be the thing that makes it work. In addition, this, bezel rotates and these eyes open, even though only one of them moves at a time. The eyes open in this version as well. So I was happy at the time of how this, with how this one works. But, as I said in the main video, somebody else figured out how to make a 4-ring version, and I like a mechanical engineering challenge. So I looked at this one and tried to figure out what I could improve. And the first thing to do, obviously, I think, is to make the load path more efficient. So having your kind of gears, your power come in over here and then have to go through a whole bunch of gears before it's actually spinning something that is a pretty big mechanical load. This is a very large ring with a very large friction surface. So that is going to be the hardest thing to move. And it's at the entire other end of this huge gear ratio. And I start with a very tiny gear, and I kind of walk my way through a bunch of different sizes. So I've got big gears, tiny gears, more tiny gears, all the way back to a big gear. And I am losing power that entire way. So I knew I wanted to fix that, especially if I needed to drive 2 whole additional ring gears and packaging. So the thing that defined this size was the servo. It's pretty large, and it's a pretty tight fit even with just this stuff. So if I go into analysis and let me change cross sections here. So with the servo, this is still a pretty tight fit. And that is what defined the size, which is roughly 2 times, I believe, what it should be. It works. There are 2 rings that spin, the eyes open, the thing spins. I was pleased with it, but the new problem statement would be, obviously a 1-to-1 scale would be great, and 4 rings moving is a much more interesting, movement. And that is what led to the new version. So this one has a few more details in it, but it is significantly smaller. It's actually 1-to-1 scale, and all 4 rings spin. And this is the one that I made the kind of main video on. So I'll walk through how this one works really quickly, and then we can dive a little bit more into it. First step is both of these, the front and the back cover, are just aesthetic housings. So they both snap into place. They snap out of place. If anything mechanical goes wrong, you don't have to reprint and repaint and do all the finishing for the back covers, or the back and front cover, which is fantastic. Just from experience, that saves a lot of time. For power input, on the other one I had the servo kind of off on the side. This one I tucked a N20, this is a Pololu motor. I believe it's called an N20 gearbox motor, but it's a very tiny, very high torque motor. I have it directly driving kind of a main gear. And that's a pretty good power delivery method. So I've got, the power input going kind of on the outside or towards the end of this moment arm. What I mean by that is it's far away from the central rotating axis, which is, for engineering reasons, that's a good approach. I then have each of these rings directly pulling power, like as quickly as I can get them to. I deliver power from this main gear to these rings. The 4 rings are up here. You can see kind of some dividing lines between them. But that was the biggest mechanical engineering change that was made, besides the gear ratios to support it, was delivering power kind of in a very clean and very short load path method. So there's 3 different steps here, and I'll hide these gear plate covers. You can see kind of each of these gear steps. So I've got main gear, and then this kind of left side is responsible for the first and the third, and the right side is responsible for the second and the first, or fourth, I guess, depending on how you're measuring it. So power comes up through maybe 1, maybe 2 gears, and then is immediately at the rings, which is a much shorter load path and uses the power that is given much more efficiently. To get the bezel to spin, it works pretty much the same way as the other one. It's just more of a snap fit. So if I hide this, where is it? If I hide this, there's just a little snap detent in there, and this guy spins with the main gear. Which again, it's just a more efficient way than having kind of a handful of gears to get to before you're actually moving anything. And the way that the eye works is as this spins, these little lugs kind of run along this ramp, and then that ramp actually kind of dives into the housing. And when it dives into the housing, this lug kind of follows it. And that happens on both sides, and the whole thing, each eyelid opens up at that motion. And that's kind of the overview of the function. To actually get the gear ratios, it's a little hard to explain kind of in a compelling video format, but the way I approached it was I knew that this bezel is going to spin 180 degrees. I could just pick that up from watching the GIF from the movie footage. So if this is going to spin 180 degrees, I know that I can use that kind of as the master ratio to calculate all of the other gear ratios from. From there, this is way earlier in the project, obviously. This is kind of the first model, proof of concept model that I did. But I knew that this bottom gear was going to spin 180 degrees. From that, and looking at the GIF, you can eyeball kind of what number of degrees these other rings are going to spin, through the full cycle. And then between 180 degrees and the eyeballed angle, you've got a ratio. That ratio is your gear ratio. And then it's just a matter of sitting down and seeing what combination of whole numbers, because it's a gear and you can't have a half gear, what combination of whole numbers, combined will allow you to get to that same fractional ratio. So I don't really know how to do that in video format, but essentially it's a bit of eyeball the angles and then plug and play with fractions until it does what you want. So you can see here I've got my 4 rings and then 3 stepped gears with a few gears here, and this is exactly what I ended up doing the actual engineering on. So you have your 3 step gears here. You've got, the kind of same exact gears, just with actual gear teeth, and then the 4 rings. And that is more or less it for the mechanical design. I think the only other feature that is really, unique here are these micro switches. So there's this whole electrical plate. If you remove the electrical plate, it's just a hand-operated assembly, and I did that intentionally because I think the electronics are either going to be, too much work for some people, or in kind of a display environment. I personally, if I'm showing this off, I like to be able to hand it to someone and have them just play with it as a toy, and not have it be like, oh, be careful that wire, or any of the stuff that goes along with electronics. So to get the electronics to work, though, in more of a cosplay setting, or really showing it off setting, I wanted it to be no microcontrollers, nothing directly controlling the timing or anything like that, because that can be problematic, and timing tends to go along with or timing can be affected by the battery voltage depending on how you do it. Like if you're timing how long the motor is spinning, if the motor slows down, your timing is off, yada yada. I wanted to just do it with like batteries and switches because it's such a simple motion. So what I ended up doing is making a very simple circuit, and what happens is when this spins into one position, this lug hits a micro switch and turns power off to the motor in that direction. And then when it spins 180 degrees, there is another micro switch on the other side that it will crash into, and it turns the motor off in that direction. And that allows you to get the full range of motion, and there's no concerns for microcontrollers or voltages or anything like that. You pop a 9-volt battery into it, and it runs at one speed. If you put a 6-volt battery into it, it runs at a different speed, but it doesn't change the overall performance. So I wanted to make it robust like that, I guess. There's a bunch of kind of holes and stuff for shaft supports. These are all pretty important just to keep it stable. These are very tiny gears, and they have a tendency to skip teeth if you apply too much force. So one of the changes that I think is between the video and now is I've actually added an extra washer in here, which I need to thin out. I sanded mine a bit, but I have a printed model that works. But I added a washer in here just to better support this piece, because one of the early failure modes of my prototypes was when you deliver a lot of power to this motor, there's not much stopping it from pushing this whole gear assembly up into this, and it kind of deflects away from each other. So I've resolved that by sticking a washer in there because it can't crush the washer. But that's pretty much all the mechanical function. I'll throw these covers back on. So I generally was able to do kind of all the things I had hoped it would do. It's a little bit thicker than I'd like, and the majority of that is actually, if I go into cross-section, the majority of the thickness is actually this motor. So I guess if there's enough interest in a completely electronics-free version, I could probably squeeze out another, 6 millimeters, maybe 7 millimeters, which I think would go a long way to making this look even thinner. But I think really impressive part, comparing it to the old one, if I put these covers back on, is I was able to do all that extra motion in about half the size. So this is the size comparison of the old version and the new version. And I'm really pleased with how the new version ended up coming together. They're roughly the same ratio. It looks like I just scaled one down, but the newer one does a whole lot more from a functional standpoint, and I think it's a lot more reliable of a mechanism. From a CAD model standpoint, it's not great. The feature tree is huge, and this isn't even the whole thing. At one point, when I was originally locking in my gear ratios, the computer became almost unusable. I was using a parametric gear ratio generator, but that means every time I reloaded the model or changed the model, it tried to recalculate the whole thing. So to solve that, I ended up exporting my model as a step, effectively doing kind of an engineering design lock on the gear ratios, and I just imported the step model as dumb geometry and continued modeling from there. So not the best practice, but it was functional, and I knew there was no turning back, but I didn't plan on changing anything. So if I had to change any of the gear ratios, I'd essentially have to start over, and that's typically why you avoid doing that kind of thing, but I thought it was necessary here. So that's all I'm going to say about the CAD model. Is it was not great, do not recommend. But that is the full model and the functionality and kind of some of the thought that went behind it. Let me know if you have any questions. Thanks for watching. See you next time.